very happy to have Henry Maxfield to tell us about Hilbert spaces and quantum gravity.
Great. Thanks, Pete, and thanks for the invitation to come up and talk about our work. Always a pleasure to make a short journey up the road, visit here. So I will be talking about the content of a couple of papers, one that came out recently and some work that will hopefully appear soon in collaboration with Jesse Helt, who's a graduate student at UCSB and is on the market this year. So the sort of main topic of today's talk will be talking about this theory of de Sitter JT gravity, which is an interesting theory in its own right. It's a simple model of quantum cosmology, some interesting speculation about microscopic realizations of Hades integrals and various things like that. But for my purpose today, it will be mostly as a very simple example to illustrate some general techniques and ideas in thinking about Hilbert spaces and sort of canonical ideas in quantum gravity that are hopefully more generally applicable. And this is a nice theory to show some of these things very explicitly without getting too lost in some of the technical details. So I'll try to keep a bit of contact with this broader context and the bigger motivation. So the motivation for me really comes from trying to make the most of some of the recent success we've had with non-perturbative gravitational effects. So things like wormholes that have been doing wonderful things for us in calculating the information content coming out of black holes, and spectral statistics, and all these nice things have been really in the context of black hole physics. But what's been done so far does have a few sort of drawbacks that mean that it's not easy to immediately apply it to some other interesting problems. So one of the things is it's been easiest to apply these ideas when you have some asymptotic boundary, or at least some weakly gravitating region where you can define your observables sort of somewhere firm to place your feet, to define a path integral, and then you sort of do some path integral in the strongly gravitating region, but it's at least easy to interpret that. And most concretely in the context of ADS-CFT, you can interpret what you're doing directly in terms of some dual CFT, or maybe some asymptotically flat S matrix or something else. It's harder to define things that are really intrinsically sort of deep in the bulk. And so the key example of that is, of course, quantum cosmology, where we don't have the freedom to go and step back outside the gravitating region because we live inside a gravitating universe. So we'd like to try and get back beyond that limitation. The other thing is that in a lot of these calculations, the sort of local bulk dynamics, what's really going on in the gravitational system isn't very manifest. So often we're using Euclidean techniques, there's some complex huddle point or something, seeing really what's going on. You know, if you're an observer falling into a black hole or something, it's not very easy to immediately stare at these calculations and say, what's going on? What have I experienced? A more specific sort of technical aim here, one of the ideas that's become important, that maybe I won't get into the details too much now, is this idea of null states, that there's some naive version of the Hilbert space, say you quantize in perturbation theory, and you have a bunch of states. The sort of important example maybe is the interior of an old black hole. But if you were to really ask how many independent states there are truly non-perturbatively, you find there are many fewer than you would see sort of naively. And this seems like a complete miracle. So, okay, it can happen from, you have some matrix within a product, it's got some very small diagonal parts that just conspire in such a way that this big matrix within a product has lots of zero eigenvalues, but it really looks like a conspiracy. And that this is something, to me, that is shouting out for an explanation. And at least one idea, or part of an explanation, is to explain this in terms of gauge symmetry, that these null states come from a gauge redundancy, and particularly actually just the non-perturbative part of diffeomorphism invariance. So that is sort of one of the key ideas to try to make that idea concrete. So we want to set up a language where we can do these things. So the sort of big aim here is to think about a way to think about gravitational Hilbert spaces in sort of a very old-fashioned way. The way that DeWitt wrote down in 1967 or whatever it was, where he had wave functions that depend on spatial metric gamma or some matter fields, really using gravitational variables, sort of drawing from this success that we've had really using semi-classical gravity. And try and construct, try and have a formalism of this kind of Hilbert space that can be used for these sorts of problems. So maybe I'll say up front, I'm not looking to non-perturbatively quantize gravity in terms of metric degrees of freedom. I think that's probably a futile exercise. There's probably some deeper microscopic structure, but we can go a long way without necessarily knowing all the microscopics. So really, I have in mind there's still some sort of semi-classical limit, some small G Newton expansion that we're doing. But what I'd like is a formalism that at 0th order in that expansion, it reduces to local common field theory on a classical background that's really has some Cauchy surface with wave functionals of quantum fields and free gravitons, say. Some systematic order-by-order G Newton expansion, and also allows us to talk about non-perturbative corrections, sort of things that will bring null states into the game. And as far as I know, there's no really standard way of discussing this language that really achieves this. But I think we've put together the ideas that we need to achieve it. Okay. So for today, maybe I'll emphasize one thing here. When we talk about a Hilbert space is a set of states and it's an inner product. And it's a positive inner product. So that's going to be one of the important things is discussing that. So, the main ideas, and sort of the traditional way, if you just go straight away, you read DeWitt. What does he do? How do we construct the states? Of course, the reason this is not straightforward, the reason it's challenging in the first place, is because we have diffeomorphism invariance, or in the sort of canonical Hamiltonian language, we have constraints. And not only do we have constraints, but those constraints involve sort of changing which Cauchy surface we're on and so forth. So those constraints are sort of mixed in with the dynamics. So DeWitt tells us that the states are solutions to the Wheeler-DeWitt equation. And you impose the constraints in the way Dirac says, as equations that on the allowed quantum states. This has an issue. It doesn't, at least immediately, achieve this aim of looking like local quantum field theory to 0th order perturbation theory. The solutions of Wheeler-DeWitt are somehow very non-local in time. There are superpositions over all possible Cauchy surfaces, and you lose locality in time. The second thing we need to sort of put on our Hilbert space is an inner product, and the one that DeWitt suggests is this Klein-Gordon inner product, but that's got a number of problems, the most obvious of which is it's not an inner product. It's not positive. So, today, we'll talk about some sort of ideas that for various reasons seem to have become much more into fashion and well-known in the last couple of years in various contexts. There's an alternative way of talking about states that's sort of complementary to the Wheeler-DeWitt solutions that I'll call co-invariants. I'll explain where that name comes from as we go along. And there's another nice suggestion for a physical inner product that goes under this name of group averaging. And so idea one is to just give you a little bit of an introduction to what these things mean and why these things are useful for these problems that I want to address. And then we'll also connect it back to this Klein-Gordon inner product and explain a little bit why the Klein-Gordon inner product is not a good inner product. But why it sometimes is a good inner product. And so in particular we're going to explain how the Klein-Gordon inner product comes from some gauge fixing condition and that it's a good inner product and in fact agrees with group averaging inner product when this gauge is a good gauge choice in some sense. Okay. So that's the idea. So we'll use JT as we go along as a sort of example touchstone to just illustrate these ideas in a very concrete and quite simple setting. So I'll just start off setting expectations with talking about just the classical theory of de Sitter JT, which turns out to be quite rich and interesting. And then we'll go through these various things. What are the states, what are the inner products, and how do we relate to point Gordon? And then at the end, I'll kind of give a list of various interesting things that we could talk about and discuss, and depending on time and interest, we can go into some more examples.
I have a question. So
yeah.
The problem with the inner product, if you go the semi-classical reason, where you say give them a buffer, is that, can you get the result, a good kind Gordon inner product? Is this
yeah, so
the semi-classical?
yeah, so it's yeah, so if the background, so if this gauge fixing, it might not be a good gauge fixing sort of globally, but it might be a good gauge fixing sort of semi-classically in the vicinity of the particular solution you're interested in, and then it's great, at least to all orders of perturbation theory. So that's a sense in which it'll be useful, is it's a little bit more concrete and easy to work with in these situations, and it'll work to all orders of perturbation theory, but it won't be necessarily good globally and non-determinatively. So you might need to glue together different sort of patches, different gauges for different states. Okay. Any other questions before we? Okay, de Sitter JT gravity. For this audience, maybe doesn't need too much of an introduction because it's something very familiar with maybe a flip of a sign that makes it slightly less familiar. So it's a three-dimensional theory of gravity, theory of a metric, and a scalar field, the dilaton. And the action looks like this. The only important thing to note is the dilaton just appears linearly, so you can think of the dilaton as a Lagrange multiplier. You integrate it out, and it imposes this constraint that the space-time has constant curvature. So for us, constant positive curvature. And this is what makes this theory simple. You can couple matter to it, and almost everything I'll say has a relatively simple generalization of matter. I'm just going to not include any matter for today, just to keep it as simple as possible. And we're going to be studying closed universes in this theory, no spatial boundaries. So the topology is going to be some circle times time. Okay, so the first thing we can do is just see what the solutions look like. What's the classical phase space? And so I would be remiss not to mention this paper of Elber and friends that came out at a similar time to us. So they studied really just the classical problem of this, and they have a slightly different perspective on things, so I definitely recommend that paper for a complementary perspective. I won't get into too much detail, I'll just sort of skip straight to what the answer is here. So first of all, because we've got this dilaton equation of motion, fixes the geometries to be constant curvature, the first job is to classify the space of all constant curvature geometries. And this turns out to actually be quite rich. So first of all, the fact that it's constant curvature means that the metric in 2 dimensions is locally determined completely. The only degrees of freedom are sort of global things. So in fact, our space-time has to be some quotient of ds2, or the universal cover of ds2, or some piece of the universal cover of ds2. And so what we have to do is just classify the different elements of the isometry group of de Sitter that we can quotient by and look at what space-time looks like. And so this basically is, we have to classify conjugacy classes of the isometry group of de Sitter, which is the 3-dimensional Lorentz group, or the universal cover. And what you land on is a picture that looks like this. So what we call the fishbone. It's unfortunately sort of half a fish. We thought that these extended both sides, and we were very happy with the name fishbone, and then we checked more carefully, like actually there's only one side, and we still couldn't think of a good name. If everyone's got a good name, then. But okay, so this sort of graph is the moduli space of constant curvature Lorentzian geometries. And the simplest piece to understand is this spine that goes left to right. And so that comes from some space-times that have a scale factor that goes like cosh t. So when the size of the universe at the neck is 1 in our units, this is really 2-dimensional de Sitter space that has a 3-dimensional space of symmetries, a full Lorentz group. But you can change the size of that neck. You break some of the symmetries, so there's only got a rotational symmetry left, but there's some 1-dimensional family of geometries you get by with a scale factor that looks like this. So that's the simplest thing. You could also have these things which look pretty simple. They again have a rotational symmetry where the scale factor goes like sinh. And there they have at t equals 0, there's some big bang or a big crunch. You've got the time reverse. And they either have a sort of scry plus asymptotic future or they have a scry minus asymptotic past, but not both. So that's these two branches, and they meet at some singular point, which is this sort of cusp geometry with an exponential scale. Maybe more surprising pieces are these ribs that come out the top of the fishbone. And these, so the best way to think about these is I've drawn this picture of, so this is the Penrose diagram of two-dimensional de Sitter space. It's like two squares. And for two-dimensional de Sitter space, we just wrap this up into a circle. So we identify the left and right of that rectangle. That gives us de Sitter. But you can also identify them up to some shift. So there's some static patch time translation symmetry. So I've drawn this is how the boosts, you think of it as the time translation in the static patch acts on these squares. You identify them up to a shift, and that gives you a different geometry. And then you can do this with not just one patch of de Sitter, but you can take the two-fold cover, the three-fold cover, or the four-fold cover. And so at each integer value of the size of the net, there's this new branch of solutions that comes out. And these, again, have a one-dimensional isometry group, but that isometry is now this static patch, non-compact static patch time translation. They don't have any of these rotation symmetries. So that's what the moduli space of geometries looks like.
What happens when you move along one of the tail spiky lines?
Yeah, so this is, so the scale factor is some number times sinh t, and that number can change. So one way to think about it is, so these have a sort of Milne type singularity, and it's the strength of that singularity.
Like if I fix the Hubble rate, you would be changing the length of the S1 at that fixed rate.
Let's see, well, Hubble rate is always the same.
Not really.
Oh, sorry, yeah. Yes, that's
Sorry, that's what we're...
yes.
I think that's
Yeah,
another way of thinking about it.
yes, yeah, that's it. Yeah, well, there's another way of thinking about it. There's some invariant that's what's the size of the universe and what's the extrinsic curvature. There's some function that's an invariant that's time independent of those two, but it could take any value. So that's okay. That's the classical phase space. Okay, so now actually to turn it into a phase space, I've just given you a one-dimensional space of geometries. I need to put something else on top of it, which is what's the classical solution for the dilaton as well. And I won't go into the details of it, I'll just tell you that there's, for each fixed geometry, there's a one-parameter family of possible dilaton solutions, at least away from these vertices. And just the normalization of the dilaton is some real parameter, and you should think of that real parameter as the momentum conjugate to the direction along this modular space. So it's the momentum that so in the paper we calculate the Piles brackets between say the size of the universe at the net, this d parameter, and the size of the dilaton solution and their canonical conjugate. So the way to think about the classical phase space is it's like a cotangent bundle of this geometry. And okay, there's something a little bit funny going on at the vertices. There's interesting things to say about that, but they're not particularly relevant for us, so I'll gloss it for now. But at least...
what is the dimension of the space of solutions in the vertices?
Of the
space of dilaton solutions in the vertices.
well, you can't talk about the dimension because it's not manifold. It actually turns... Oh, sorry, at the vertices... Yeah, so
then the space of dilaton solutions.
Yeah, sorry, yeah, the space of solutions is still one-dimensional, but it's... Yeah, so for example, if we look here at this vertex,
yeah,
then the solutions are constant along the curves of some integral curves of some symmetry.
yeah.
And at this thing, there's an SL2 of symmetry, so it's a Lorentz group. There's a three-dimensional Lorentz group of symmetries.
Yeah.
And you've got to choose which symmetry you leave invariant. So what you're doing is you're choosing some element of the Lorentz group, and that can either be a rotation, and if it's a rotation, it sort of moves you along here, or it can be a boost, and that moves you up here. Or it could be sort of null, or there's actually a funny entry point down. But yeah, so it's one-dimensional, but there's a sort of transition between a boost and a rotation. So that's why it's sort of
I think I lost you a little bit here, I'm so sorry, but when you're talking about like, on top of what the metric can do along the fish, at every point you have a multi-parameter family.
Yeah, so let's just stay away from the vertices for now. There are sort of measure sets that don't make too much difference. If you're away from a vertex, give me one of these geometries. There's a one parameter family of Dilaton solutions. And so let's take this example. So we'll take the geometry A is equal to B times cos T, and I think I previously wrote it. And the Dilaton, it turns out to be a solution. It has to be some number, curly phi times sin T. So again, it's just a function of time. It keeps this rotational symmetry manifest. And so the solutions locally are parameterized by two parameters, and these are true. And something similar is true at every other point, except the vertices, but
and the boundary condition fixes some combination of BM phi, right?
boundary condition. I'm not setting any boundary
Yeah,
condition.
but if you were to set boundary condition,
Say if you had some initial condition
Yeah.
or some, sure.
but not
Yeah.
both.
Let's see, B and phi. Well, classically you can choose them independently. Yeah, so the classical phase space is two-dimensional. Think of it as this fishbone times a real line. That's not quite true again because of the vertices, but it's true locally. And so classically it's a two-dimensional phase space. Quantum mechanically, our expectation would be, because it's a cotangent model, our expectation would be that the states are wave functions that are valued on this geometry only. So we just depend on B and not this kind of phi.
I think, yeah, the only thing I was saying is that if you fix the, let's say an asymptotic end state,
Yeah.
then you can fix the ratio between, suppose you don't fix what B and phi are, you only fix the data on an asymptotic slice, that fixes the ratio between your curly phi and B in that equation, right? But it
sure.
doesn't fix B and phi in that
Yeah,
equation.
it's his usual thing.
Okay.
Quantum mechanically we choose a half-dimensional space.
Okay.
Okay, so that's the phase space. Okay, so that's the end of the classical discussion, more or less. So, okay, going back to the big picture, just talk about the philosophy of how we're going to try to quantize a theory. And so the idea is we're going to start with some larger Hilbert space, where we haven't imposed the constraints. So think of this as wave functions of all possible spectrometric and any Maxfield configurations without any restrictions on what they look like, with some trivial sort of L2 type inner product. But to get the physical Hilbert space, we have to impose the constraints. And so we think about the constraints in this way of thinking about things as some operators that act on this unconstrained Hilbert space. And these constraints generate gauge transformations. And so what we'd like to do is we take these two ingredients that are given to us from somewhere, and we want to impose the constraint B0 and get some physical Hilbert space. We've got to decide how are we going to define what the physical states are, or how are we going to work out what the inner product is. And maybe I'll just contrast this briefly, I won't say too much about it, but another way of thinking about this would be to impose the constraints classically, which is work out this physical phase space like we did on the previous slide in the classical theory, and then quantize the phase space after imposing constraints. It might be different, and in particular for these non-perturbative effects, there are non-perturbative effects that are not captured if you do these other ways. So I think this way is a better way to do it. I can comment on that at the end. Okay. So let's talk about this in this specific example of JT. So here we have some metric, so you use some ADM decomposition of the metric, and so our variables here, our sort of configuration space, is this A, which is like a scale factor, it's some function of the angle on the circle, what's the size of the circle, and then the dilaton as a function of the circle. And so our unconstrained Hilbert space is just any wave functions of these two wave functionals that depend on these A and R. And we have some conjugate momenta. So just the notation here, I will use P for the momentum conjugate to the scale factor, and K for the momentum conjugate to phi. So a nice reason for this is that K is interpreted as, roughly speaking, the extrinsic curvature, and K is a sort of curvature kind of letter. So K, and it's also a sort of momentum kind of letter, so K is this momentum conjugate to phi, and P is conjugate to A. Okay. And then we have these Hermitian operators, it's Hamiltonian and momentum constraints. The only comment I'll make about these is that we should note that these things are linear in phi and in p, and p note is linear in the time derivative of phi. So the fact that these are linear in phi and p is the sort of Hamiltonian version of the fact that our action a few slides ago was linear in phi, and so phi is a Lagrange multiplier. And that was the thing that made the theory simple. So this linearity in those variables is what's going to make the theory simple and so on. So for essentially all the talk, I think I'm actually going to make this theory yet simpler. It's not simple enough for me yet, which is to go to some mini superspace version. As sort of justification of this, I can give afterwards maybe that this mini superspace truncation is actually exact, or at least it's exact in the part of the theory that it captures. So a way to think about this is we do some gauge fixing to so that our Cauchy surface has constant extrinsic curvature. It turns out that you can do that gauge fixing exactly mechanically, and so we're actually only left with a finite number of variables. So a two-dimensional configuration space, which is the size of the universe, the scale factor, so it's really like a two-dimensional FRW universe, very simple, and then just dilaton that depends only on time and not on the angle. And the way to think about this dilaton is it's really the zero mode of the two-dimensional dilaton. We're not setting constant dilaton. Okay, it's a minor detail, but anyway, we've got this two-dimensional configuration space. So our unconstrained Hilbert space in this mini superspace truncation is just functions of two variables, and the A should be positive, and the dilaton can take any value, so it's wave functions on our half plane. And we're left with just one constraint, which is the...
You wrote A prime equals 0, but one is a consequence of the other, right? You don't need to say that these are two independent conditions.
These are two independent conditions. So one of them says that, so A is this is prime means derivative with respect to the angle. So setting A prime equals 0 says that the theta, the coordinate on the circle, is going to be proportional to the proper length. Yeah. So it's sort of the thing we're using to fix the momentum constraints. And then K is the extrinsic curvature. So setting K prime equals 0 is how we're solving the Hamiltonian constraint, or at least most of the Hamiltonian constraints, with the exception of the 0.
So in a de Sitter geometry, these will be in a...
Yeah, so I mean this A prime equals 0, this first one, is purely intrinsic in the slice.
Yeah.
It tells me nothing about and the K prime equals 0 is purely extrinsic. It tells me about the embedding of the Cauchy surface in the full space-time. So that's really...
Yeah, so they will be, but they will be equivalent if phi was constant on the...
Right, yeah, so yeah, actually what's going on is that the non-zero modes of phi, the spatially dependent modes of phi, in this gauge fixing are actually fluctuating uncontrollably. And that's the right way to interpret this. Yeah, so some people have said that this mini superspace is exact, but I think that this particular one, the right interpretation, wasn't justified.
Still kind of broad gauges in name.
Yeah, so this gauge fixing, this fixes the sort of non-zero modes, so the Hamiltonian constraint and the momentum constraint that depend on the circle, and so these two things, they fix the spatially dependent modes of those and leave behind the the sort of the rigid time translation and the rigid rotation. The rigid rotation here is in the pure gravity theory is trivial. It does something still if you have matter, but it's completely trivial here. And so the only thing we're left with is a single constraint, which is the Hamiltonian, now the rigid Hamiltonian constraint, where we evolve by the same time in every point. So this theory, the only drawback with doing this gauge fixing, or the main drawback with doing this gauge fixing, is that it turns out that there is no Cauchy surface of constant extrinsic curvature in these funny ribbed branches of the geometry. It's kind of, there are space-time with no geodesics, no closed geodesics, or not even any constant extrinsic curvature slices. It's okay, something can happen, and it happens to those geometries. Okay, so we're left with a classical phase space that now just has these three branches that we'll call the bang, crunch, and bounce geometries.
So I'm a bit confused about that. If I take K to be enormously large, that's like a circle that's very tiny, wouldn't that close?
So it's got to be a Cauchy surface, so it's got to wrap.
Oh, you want it to be an entire Cauchy surface. Okay.
But yeah, okay, so we observed previously that we had this nice property that the constraint was linear in the dilaton and in P, it's the time derivative of the dilaton. And so actually we can make use of this by Fourier transform, going to the conjugate momentum to the dilaton to make our life extremely simple and solvable. It's worth bearing in mind here that this is the special thing that works in this case, and we won't, for a general theory of gravity, have access to this, but this is going to make everything completely solvable for us. So we Fourier transform, and now this constraint is a first order differential operator, because it's linear in the momenta. Now thinking of phi as a momentum conjugate to k. And actually this, it's extremely simple. You can think of this as a generator of boosts in the AK plane. So this is what this looks like, and we can think of each trajectory of these of the flow generated by this Hamiltonian. Each trajectory corresponds to a different point in our phase space. So there are trajectories that live in this Rindler wedge that follow the constant a squared minus k squared positive, and they correspond to these bounce geometries, and similarly there are bang and crunch geometries. And so we can make this even more manifest, it'll be useful in the future slides, by going to some Rindler coordinates that make this symmetry completely manifest. And so you use some Rindler type decomposition, and then the Hamiltonian is just a translation in real time. So this is very simple. I should probably briefly comment that there is something that I'm sweeping under the rug and will continue to do so unless you vehemently object, which is there's this A equals 0 boundary. There are interesting things to say about that, but it's not the main topic of the talk, so I'm going to just ignore it unless you force me to address it, or I can comment at the end. So you do have to deal with it. We've got, I think, what's a very natural way of dealing with it. We'll ignore it for now. Okay. Okay, so this is the theory. We've got Hilbert space, wave functions, and a constraint. We want to impose that. So, the first thing we've got to do is identify what are the states, the physical states, after imposing the constraint. And so, top left is the sort of traditional way that we told us to do it. You solve this equation. You impose the fact that the constraint annihilates the state as an operator equation. And we'll do that explicitly for this JT Hamiltonian, the next slide. So the first thing I'll go to the sort of examples. So these things show up quite naturally. For example, if you do some path integral. So I've drawn a couple of examples. So on the left, think of a path integral with ADS asymptotics, with some sources turned on and so forth. And then we ask about the path integral where we have these boundary conditions asymptotically at the conformal boundary with some sources. and then we choose some boundary conditions on a quotient surface, which says we fix the metric and matter fields with some configuration, and we do that path integral, and we think of that as a function of, let's say, the intrinsic metric on this slice. That will solve the Wheeler equation. So you, naturally speaking, a set of boundary conditions doing the path integral gives you a solution of the Wheeler equation, gives you what I call an invariant state. I call it an invariant state because it's left invariant by gauge transformations. In this example, with a single constraint, time translations leave you invariant if the Hamiltonian annihilates the state. Another example very similar is the Hartle state. Thought of in the same way. Okay. So the first thing I want to emphasize is that this is not the only way of doing things. And actually, there's a strange historical thing that this is maybe the first thing that people reach for in gravity, but it's absolutely not what we do in electromagnetism or Yang-Mills theory or so forth. We do something else. So at least here is one different thing you can do, which is rather than imposing these operator equations, you can keep all the states around, but you think of the physical states as equivalence classes. So any wave function is fine, but two wave functions that are related by a gauge transformation, you think of as the same state. This is kind of exactly what we do when we're doing classical gauge theories. Actually, if we do classical gauge theories, we do both of these. Right? First of all, we impose Gauss's law has to be true, and we also identify gauge configurations related by some gauge transformation. So we do both. The fact that we do one or the other is the sort of same thing as the fact that wave functions are functions of half the phase space variables. Same kind of thing. So, okay, we impose these equivalences. And the name covariance I'll explain momentarily.
And actually, could I ask about the A equals 0, the atypical boost? So, are you thinking of it as a non-unitary operator? Or,
Yeah, so you allow the gauge transformation to be non-unitary in the right way, and you get a sensible theory by doing that. The physical interpretation is to say, I can comment on that. I don't want to get into it.
Yeah, that's
Okay, so this is another way of doing things. Things that this is concretely useful for are solving this problem of having states that are somehow local in time, that this Wheeler equation doesn't do very well. So one example of a state we can think of in this language is a geodesic state, say in GAT. So we've got this wave function that depends on scale factor and intrinsic curvature, and so what I can do is just choose any wave function I like, because I've not imposed any constraints, and I'll choose that wave function to be a delta function of 0 extrinsic curvature and the universe some particular size. And now I think of this as a wave function that's just a particular representative, a gauge fixed representative, if you like, of some equivalence class. And this is and we can, a similar thing we can think about, there's this nice paper of Witten, Note on Canonical Gravity or something that talks about this maximal volume gauge fixing that I'd be happy to talk about afterwards. You can think of that in a similar way. You're choosing some particular wave function that has 0 mean curvature, but it doesn't have to solve the Wheeler equation, and you can think of this as a particular gauge fixed representative of a equivalent class of states. Okay. So there are these two ways of talking about states. They're not unrelated, they're dual. They're dual in the sense of linear algebra. So that's what this co means. So invariants are things that are invariant under gauge transformations. Co-invariants is the linear dual to them. So what that means is that there's a natural bilinear or sesquilinear pairing between invariants and co-invariants. The reason for that is that we can, if you just try to naively take the inner product over here, so your constraint, the Hamiltonian, will take me out a continuous spectrum. You try to take the inner product, there's some delta function of 0 energy, some nasty divergence that shows up, just like scattering states are not normalized, not normalizable. And similarly, if we try and just naively take the inner product on covariance, depends on if we add some sort of pure gauge piece, it'll change the result. So it's not a physical thing to do. But if we pair the two things together, then we do get something finite and sensible. It's sensible because if we add some pure gauge piece, add some gauge transformation, then it doesn't change this inner product. using the fact that the invariant state is annihilated by the constraints. So these two things. Okay. So let's just do this quickly in JT. I won't maybe read everything on the slide, but we'll just comment on solving the Wheeler-Wheeler equation is easy because it just tells me the wave functions depend on this one invariant, k squared minus a squared. There's actually 3 pieces, one from each sort of the top middle wedge corresponds to these crunching states, the Rindler wedge, and the bottom middle wedge. And another sort of this example of asymptotic states, the path integral defining a covariant. Another example of that here is these asymptotic states. And so these are the things, if you take the usual boundary conditions that people use, say in hyperbolic, ADS, Euclidean JT, these boundary conditions that define partition functions, these have an analog here that have been considered in many cases in the center as well, and they give you some wave functions, some solutions to Wheeler-Wheeler that you can work out. And they look like plane waves in this invariant a squared minus k squared. You can also do this co-invariance thing. So to make this very, very explicit, let's talk about use these sort of Rindler coordinates, where the Hamiltonian is just a translation in some coordinate u. And so what we want to say is that a state, any wave function that depends on these two variables, is equivalent to a wave function plus a derivative. And at least if you impose the right fall-off conditions, okay, there's some analysis, sort of functional analysis stuff you have to do to be, if you want to be really careful about this, but at least naively, what we can do, if we add a total derivative, we can change the function in any way we like, except we can't change the integral over the all u. If this gauge transformation falls off. So there's a single parameter. So just like over here, there's a single parameter that defines the states. Here, there's also a single parameter. It's this invariant. And in fact, it's not coincident. Okay. Yeah, and maybe just to comment, this co-invariant condition looks extremely simple here. If you were to try to do this directly with quadratic constraints in momenta or in realistic theories, it'll look a lot more complicated, and you really don't have a lot of hope of doing this sort of completely, but you can do it. You might have to resort to some classical techniques.
Is it any like a particular thing about this particular system? Why you go with the momentum space for the don't simplify?
Yeah, it's the fact that it's linear in the Denison. Again, it comes back to the fact that it's linear in the Denison. So, or the other way of thinking about it is the geometry is rigid, so we use the variables that describe the geometry. So the size of a circle, the extrinsic curvature, geometric variables. Might have to accelerate a little bit. Okay. Okay, so that's states. The last thing we have to introduce are inner products. And so the useful sort of bit of mathematics that we need to remember here is this fact that the invariant states and co-invariant states are dual. Maybe I should credit the language of invariant and co-invariant. The idea goes back to the 80s or 90s. The language, I think first appeared in this paper of Longo, Pennington, Whitten, Chandra Sekaran on an appendix. It's a nice appendix that explains all of these things. So I should give that credit. Anyway, so this, to talk about inner products, we're going to use this duality. So what we want to observe is that, so first of all, we want to impose an inner product, but second, we've got these two different ways of talking about states, and so we want to choose, is one better than the other? Are they different? But it turns out that finding an inner product and sort of choosing between these two possibilities are solved at the same time, because an inner product is the same structure as a linear equivalence between the two. So the reason for that, maybe we'll look at these equations over here. We'd like some inner product on these co-invariant states. The way to construct an inner product is first of all, you choose some map eta that takes one of these co-invariant equivalence classes, and it gives you a solution to Wheeler-Wheeler, an invariant state. And then because I have this pairing, I can use that pairing to define an inner product. So this equivalence is the same thing, or another way of saying it is that I choose my matrix elements to be, sorry, I choose my inner product to be the matrix elements of some operator eta, and I think of this operator eta as a thing that maps these cosets on the right-hand side to these solutions to wheel it on the left. So it's sort of like a projector onto gauge invariant states. So if my gauge group was a compact gauge group, you could literally use a projector. But here it's not, it's a non-compact group, so you can't literally do that, but you can do the next best thing. So we'd like this thing to be an inner product. So it should have a few properties. It should be Hermitian, so you have actually a sort of sesquilinear inner product. It shouldn't care about what representative of the equivalence class we use, so it should be sort of compatible with the constraints in this sense, and it should be positive. Good. 440 is the... Very good. Okay. So, and yeah, the last thing to note is that this, well, maybe I'll just move on to get to the important characters. Okay, so this inner product, eta we're using, at the moment it looks like there's a huge number of possible choices. So this is called the rigging map in this various bits of jargon. This whole procedure has got this name of refined algebraic quantization, and there's lots of literature in the 90s and so forth. But one of the important results is that there's this good candidate for eta that for a general gauge group, we can think about this eta is constructed by integrating or averaging over all possible gauge transformations. So if this is a compact gauge group, this would give you the projector onto the invariant states. But if it's a non-compact gauge group, it's something that's a little bit nastier, but it makes sense. So let's take the example of a single constraint here, our Hamiltonian constraint. We average over the Hamiltonian constraint, integrate over all the real line, and we get some delta function of the constraint. So it's something that's sort of just imposing the constraint very directly. Importantly, it manifestly has all the properties we want. In particular, positivity. In fact, the delta function is a positive distribution, tells me that this is going to be positive. Yeah, and there's various other bits of justification for why this is a good choice, DRST and so forth. But anyway, this is a nice choice. So, you can do this very explicitly in JT. Again, maybe I won't get into the details of the equations, but for example, you take one of these geodesic states and you average it over this trajectory, and all it's doing is it's smearing over this trajectory, so now its delta function was a delta function at a point, now it's a delta function on a curve. So you get this a single delta function out. And we can then use this to calculate an inner product and so forth. And now, sort of indirectly, because we've got this relationship with the solutions of Fourier-DeWitt, by thinking of eta as a map of equivalence, it's something a little bit indirect, but we can, this theory is simple enough that we can very explicitly get now an inner product on solutions of Fourier-DeWitt. And it has this sort of BDB measure, which might be familiar from sort of gluing trumpets measure in JT and so forth, and that's no coincidence. So this is the natural measure that comes out from this procedure. Which, if you just quantize the constraint first, then quantize, you wouldn't really have any guide to what the measure is or how to interpret the normalization of the states. Okay. So, the last important comment about this group average inner product is it has a straightforward interpretation from the path integral. So if you want to compute the inner product between, for example, two states that have definite spatial geometry, you just have to do the integral over all possible Lorentzian spacetimes that are bounded by this. It's important here that actually you allow both forward and backwards time evolution, so this integral is over the real line, not just positive values. But more or less, this is the procedure. It's something you can do semi-classically very nicely, and it's a very natural thing to do from the path integral. Good. Yeah. So for our one-dimension, for our single constraint example, this path integral is meaning e to the minus IHT, and then we're left with just an integral over t. Okay. So now this connection with Klein-Gordon comes in that I'll briefly touch on in the last 8 minutes. Okay. So the importance of the Klein-Gordon inner product comes from when we try to slice one of these path integrals. So to Hilbert spaces for a living, what they like to do in the path integral language is they allow us to slice some larger path integral and interpret the result as a sum over intermediate states. So that's what we'd like to do. We want to take, for example, an inner product between an initial state and a final state and ask about factoring it over some intermediate states. And so we want to cut on some Cauchy surface, but now, unlike for common field theory, where you get to choose a Cauchy slice to cut on, now the diffie-Hellman invariance means that we have to sort of specify where to cut. So there's some gauge fixing condition, say chi equals 0. Chi equals 0, surface is going to be this slice we're going to cut. And so in the path integral, we insert some delta function that fixes the Cauchy surface to be our cut, and then there's some measure, Falaev-Popov determinant type vector that we have to include. And then our path integral falls into 2 pieces. So there's the bottom piece, which is you start with your original state, you do some path integral, and then you insert this delta function to sort of evaluate it on this gauge fixed slice. And so the eta piece is doing this path integral over the bottom piece, and then this kappa map, which is roughly the inverse of eta, is the thing that's fixing us to this particular gauge fixed slice. And so we think of this, we started with the state gamma 1, which is one of these covariates, an element of the equivalence class, and we applied this operation, and it gives us another representation of the same state on a different slice. So it's done the evolution for us, in other words. It's told us how to evolve our initial data under a different gauge surface, but now on a And if this gauge was good and everything's working out great, this should factor amplitude. So we should have this, we should be able to take the bottom half of the path integral and add the top half of the path integral, and it should glue back together our original path integral. So this formula we had before, that maybe I didn't comment on too much, of the fact that this kappa is a generalized inverse to the group averaging, is geometrically just the statement that we can cut and glue path integrals in a neutral way. Okay. So, a little abstract, trying to make it a little bit more concrete and more concrete again, is we'll choose our chi to be a function of the metric itself, so some function of superspace, if you like. Then what we land on is precisely the Klein-Gordon inner product as the way we wrote it down. So gamma equals 0 is some hypersurface in superspace. This is the Klein-Gordon inner product, so you might be familiar in this form. There's some normal derivative to the slice you're cutting on, and there's some difference of this acting in the past and the future and so forth. So we can think of this as a map kappa that first of all includes a delta function. So when we do this integral, we're not integrating over the entirety of configuration space. We're integrating over a particular surface, a gauge fixed surface. So there's a delta function to restrict us to the surface, and then there's a momentum, a normal momentum which inserts these derivatives. And the way to think about this is in this language we had at the cutting. The delta function is a gauge fixing piece, and the insertion of the momentum is precisely the Falaev-Popov determinant that gets us the right measure. And so this looks like we've done a good job, we've got a nice measure. And you can do something a little bit more general here. The Falaev-Popov determinant, in this case with a single constraint, is the time derivative of the constraint. And if I were to rescale the constraint, for example, then this thing would be invariant. It shouldn't depend on what gauge choice I make. Okay, but it has a problem here that it's not positive definite. Okay, so we've got to explain for this gauge fixing procedure that look kosher, why didn't we get something that was the same as the original inner product? Something that was physically a good inner product. And the answer is that really when you do the Falaev-Popov procedure, you get a determinant, but the real measure is like the modulus of the determinant. You don't automatically, the ghost thing might give you a sign here and there. And so you sort of by hand sometimes might have to fix this sign to be positive. And in this example, this Falaev-Popov determinant, which is just the direction your trajectory crosses the gauge fixing slice, it could take either sign. And so the sort of good modes that cross it in the right direction are the positive frequency modes, and the bad modes are the negative frequency modes. The other thing that can possibly go wrong here is a so-called Gribov ambiguity, which is actually does this gauge slice pick out a single representative of every orbit, and that's usually it's a hard problem in gravity because it's hard to choose a universally good gauge fixing that does the job for every configuration. In fact, I don't know any example in any realistic theory of gravity. Okay, and so you might try to just put in some modulus by hand, and that's fine semi-classically, but it's not good. Not observatively, doesn't make sense. Okay, so let's just, it's a little bit abstract, let's do something in the SIMPLE-JT. So maybe a simpler example that's not quite this Klein-Gordon thing, but closely related, is to fix the slice of some fixed extrinsic curvature. And so, say if K0 equals 0, that could be a 1 to constant trade-off, you're choosing to fix to a geodesic. So you're mapping a solution to the Wien-Lewis equation, and you're asking to fix to a geodesic. And so there's some measure factor here that is this value of Popov determinant, the time derivative of the gauge fixing condition, which is this factor of A, and this is precisely the measure factor we saw before. So if, for example, if K equals 0 on the geodesic slice, this is this BDP measure. And so there's another way of understanding this measure factor. But this gauge fixing condition actually it's not great. It's got this sort of Gribov problem that it doesn't capture all trajectories. There are some trajectories that just miss the gauge slice completely. And there are a bunch of other choices we can make. Unless you do something really contrived, it's hard to pick one choice that does the job once and for all. The last comment I'll make about this is that we also reanalyzed the real traditional Klein-Gordon inner product, which was used in various papers, including this first one by Malda-Sanita reaction Yang. And you can evaluate this explicitly in some basis, and you get something that's just, it looks kind of like a mess, non-perturbatively. If you take some semi-classical limit, which is some large parameter limit, then you can interpret these things nicely as some negative frequency mode, or some mode that never crosses the gauge slice, or some positive frequency mode, and it looks nice. But really that only works in some semi-classical regime, and more generally it's not producing the physical inner product, which is the group average inner product, which is positive.
Is it because you don't have a complete set of states, because you don't capture?
Yeah, it's because it's
like a identity operator and so forth.
yeah, it's sort of a mixture of these problems that the measure is not always taking the right sign, and also that there are some configurations that just never cross the gauge slice or cross it multiple times. In fact, it's another thing that can happen. So that's why it doesn't quite agree. So this summarizes the main ideas. We've got these two sorts of states, and they're useful for different things. So these invariant states are quite nice, they crop up naturally, but they have this problem of being non-local in time. But the co-invariant states are sort of gauge-fixed thing, and they localize you to a Cauchy surface, and that's a good route towards getting back this description that looks like common field theory on some fixed surface of zeroth order perturbation. There's this group averaging procedure, which is a sort of principled proposal for an inner product, but in some cases it might be a little unmanageable. That this sort of inverse, these Klein-Gordon-like inner products are in sort of concrete calculations, might be more pragmatic, but they have these problems with the measure and with these sort of Gribov ambiguities that you need to have in the back of your mind whenever you use them. Which are sort of well known of these properties of negative normal states and so forth, but now we've really got a physical handle on when these problems show up and when you should worry about them. And there are a bunch of things that we can talk about. So we've mentioned this fact that the constraints aren't essentially self-adjoint, this A equals 0 boundary. This forthcoming paper will describe a lot of ideas in the BRST formalism of how this embeds, and so there's a much more general thing you should do, which really we do in ordinary gauge theories, which use a mixture between these two ideas of invariance and co-invariance, and these things all package together very nicely, and they're actually a very practical calculational tool in BRST. There are various other things we talk about non-perturbative quantum effects in this description, and why it's important to quantize first to capture them correctly, and the ideas of how null states can be incorporated as sort of residual gauge transformations in these co-invariant states. And there's a bunch of interesting things in the SIMPLE-JT, but think I'm probably over time, so I should stop there, and if there are questions about these things, I'd be happy to take them. Questions, but maybe probably accelerate a little too much.
Is it completely obvious that when you have these non-standard quantum effects from quantizing first, that that's like right? I instinctively think it is, but are there any others? Can you see the same thing from like path integral or something like that? If I say matches that better.
Yeah, the path integral. Yeah, if you I guess you could probably, if you do constrain first, you could probably define some on-shell or sort of partially on-shell path integral.
Yeah.
That is a path integral over the constraint surface. Maybe you could do something like that. But certainly the usual way that we do the gravitational path integral, which involves integrating over off-shell thing, but in particular, having Euclidean saddle points, for example, are interpreted in this. If you have a Euclidean saddle point, typically that will not be captured if you constrain first. But
can you explain that a little bit? Can you give an example?
yeah, I'll give you an example. So, very prosaic example. Think of our Hamiltonian as like a particle in the potential. But we're going to impose this as a constraint, and we'll have the potential be something that's negative over here, has a lump, and is positive over here. And so we have some allowed states on the left-hand side and some allowed states on the right-hand side. So there's some scattering wave functions that come in and out. If you were to do the constrain first, then your phase space would have 2 points. You would have the state that bounces off over here and the state that bounces off over here. And maybe you would naturally end up with, say, in states, in from the left and out from the left, and these two states would be equal to one another, and then you have in from the right and out from the right. But of course, we know if you have a quantum theory and you have an in state, then there's some tunneling that goes on, and then there will be some e to the minus s out from the right piece over here that you'd be throwing out if you quantized, if you constrained first. But you can capture this, for example.
No, I understand this example. I was more wondering about your statement about gravitational saddles.
Yeah. So yeah, there is a gravitational saddle point for this, which is a configuration that comes in over here, and if you like, it has real lapse. It takes a real amount of time to get to the turning point, and then you have some imaginary lapse over here. It takes some imaginary time to go under the barrier, and then it has real time again. And so this really comes from a complex. This is a one-dimensional space-time metric, and it comes from a complex space-time metric. And yeah, you could make this look more like a theory of gravity with extra dimensions too.
So you mean to say that if you really do the path integral correctly, you are quantizing first, right?
If you do the path integral in the way people usually do the path integral, then yes, you're doing something close to this quantized first theory. Yeah, so in fact, like in this example, when you do this path integral, you integrate over, say maybe you take some. So integrating over space-time, over different lengths of time, is doing that group averaging thing, and so that integral is the thing that imposes the constraints. But you are doing integral over off-shell things that don't satisfy the constraints, and it's only when you look for equations of motion that it should be independent of the lapse, the change of the amount of time you evolve by, that you impose the constraint as in that case, just a semi-classical equation of motion, but the full integral should impose it as this quantum mechanics.
So most of the examples you showed us here is like for the calculation for the mini superspace for the tail of the spectrum, right? Like near the end.
It doesn't have to be near the end. It could be anywhere on these. It's just not on the there's not all these extra
Okay, okay.
branches. Yeah.